In a general vector space, it doesn't make sense to talk about multiplying vectors together. However, in LVW, the vector space of linear maps from V to W, it does. And that's because we can define the multiplication in terms of a composition of maps. So suppose T is a linear map from U to V, and suppose that S is a linear map from V to W. Then we can define the product. So this is ST. Now this is going to be a map from U to W. And so we define it to be the composition of these two. So that means that, how do I define ST? Well, I always define a function by saying what it does to an element, right? So what does this do to the vector U? Well, first, actually here, let me back up. First, you apply T to U to get an element of the vector space V, and then S is defined, so you can apply S to the output. So diagrammatically what's going on is we've got U, and T is mapping elements of U into V, and then we've got S, and S is mapping elements of V into W, and then we're looking at the composition between these two right here. So this is S composed T, going straight from U to W. And it's interesting or important to recognize that even though you see S first and then T, the way that you read it, it's actually T happens first, and then S is applied to the result, so that happens second. And so in particular, that means that the product might only be defined one way. So TS may not be defined, right? In order for TS to be defined, well, that would be doing S first. So that means that the domain of T would have to equal the codomain of S. So in other words, U would have to equal W. But if U doesn't equal W, then maybe TS isn't defined. And we will see that once bases are given for each of these vector spaces, then any linear map T from V to W is given by matrix multiplication. So if you've been wondering all this time, hey, this is a linear algebra class, when the heck are we going to get to matrices? Well, this is where the matrices come in. Matrices are correspond to linear maps between vector spaces. And so just to make this a little bit more precise, if we take, say, V here to have dimension n, and W here, to have dimension m, then there exists an n by m matrix A. Oh, sorry, I wrote those backwards. An m by n matrix A such that T applied to V is given by matrix multiplication by A. Right? And then in this case, if, say, S was given by matrix multiplication by B, then ST applied to V would be B times A times V, right? And so the thing that you know about how matrix multiplication is not commutative stems from this fact about how the composition of linear transformations, it might do different things depending on the order in which you do those mappings.